Assalamualaikum all. This is the last chapter or topic for this semester, and this is about overlapping generations model. Perhaps some of you have heard this model because this is some articles that I assigned to some of you are related to overlapping generations model. Now, what does it mean by overlapping generations model and why it is named like that? So basically, it is a kind of model in which, if I try to show it to you, let's say in the life we have two different periods of lifetimes. So from if this is the lifeline here, starts from 0 up to point t, and then point t plus 1 at the end. Yeah. So now from point 0 to point t, maybe the person is born and then becomes young and then is able to work. So here this is during youth, okay, and then during old age, okay, old age. But during this period of time, this person during his youth, he must have his parents who are at old age as well. Okay, so we have two different types of generations, young and old, in the same time period between 0 and t. So same goes to the second period between t and t plus 1. When we are old, then there will be some people who are young. So we have youth here. Okay, so that's why we can see two generations overlapped, and it happens in the same period of time. So that's why it is called overlapping generations model, or usually called as OLG. Now, I'm going to explain to you, or I'm going to show to you the simplest form of OLG, so that you know how to read, certain economic journals when it comes to theoretical paper, if it relates with, OLG. Okay, now let's look at the setup of the model itself. So we consider time that it takes the form of discrete intervals. So 0, 1, 2, 3 up to, whatever we want to have. And then in this economy, we assume that, okay, we have population, okay, and we have overlapping generations of individuals, like I said earlier, okay, and each of them faces a finite lifespan of two periods, okay, that is young and old adults generations, and then a household born in period T is young during period T, and then once he or she move to period T plus 1, he becomes old, okay, and he works during young and then retires during old adulthood, okay, and the population of people or individuals in the economy in period T, okay, we have the total number of people here or individuals given by capital N T, and then this population grow at the rate of small letter n positive, that means, okay, we have this. So I'm sure you have seen this in Solow model. Now in the economy, we have perfectly competitive firm, and these perfectly competitive firms produce homogeneous good, okay, and these homogeneous goods, after being produced, will be consumed by individuals' household in both periods of their lifetime. So it means, like I said just now, okay, the person live two periods of life, starting from 0 t becomes he is young, and then up to point t plus 1 he becomes old, and then at the end of t plus 1 he dies, for instance. But within these two periods, he consumed here, and then he also consumed here, denoted as C, CT and CT plus 1. But during young period, okay, this person work and then earn income, isn't it? Then during old period, he retires, so he doesn't earn any income. So how he's going to consume if he doesn't have any income? So that's why, in order to finance his future consumption in period T plus 1, he needs to save some part of his income in the form of saving at any financial intermediaries, let's say banks, okay? So all of the individuals in the economy will save some amount of money from their income during young, okay, during youth, and then in return they receive this much of units of output in period of t plus 1 in the next period when they are old for every unit they deposited in period t. Okay. Now, this is just a general setup of OLG, but now in general, in this economy, okay, we have individuals household or household, yeah, and then we also have firms. Okay, so for individual household, I have shown you the the general idea, but I'll show you specifically the setup of individual household, and then I'll show you specifically the setup for the firms. Okay, let's look at the specific setup for the household where we have utility function here. Okay, so the lifetime of utility of a household is given by expression 1. So you have ut equivalent to u ct plus beta u dt plus 1. Yeah? So ct is consumption during youth. Okay, consumption during youth. Okay, dt plus 1 is consumption during old age. And you see beta here. So beta here is between 0 and 1 in terms of value. But what it is what we call discount factor. Okay, it is what we call discount factor. So obviously, a lower beta, okay, means that individuals assign lower weight to utility accruing from future consumption simply because they are more impatient. Okay, so it means, okay, if you put a lower weight here, let's say 0.2 for consumption when you are old, yeah, that means you put less importance to the consumption at old age. So if this one is 0.8, okay, then you put more, weight on consumption in the early stage of your lifetime, isn't it? Or, you can make up a lot of things here. For instance, yeah, if you are very good in utility construction, you can also have 1 minus beta uct plus beta dt plus 1, yeah, okay, you can also have this, but here it seems that the weight is given by 100% for the first period of lifetime in terms of consumption. But anyway, that's just additional explanation to understand what does it mean by how do you interpret beta or discount factor. Okay, now what's the condition of this ut? What's the condition of this utility function? So the function ut here, we have uct and then we have udt plus 1. So for every single thing here, what's the conditions? Okay, so the first condition is it must be the condition is that it must be twice continuously differentiable. So what does it mean by twice continuously differentiable? It means if you differentiate utility function in one here for the first time, you can get answer. Okay, then you differentiate it the second time, you can get answer. You don't get answer something like step function or whatnot. That's what it means. Okay, so in order to understand more about continuously differentiable, okay, for any function, try to search YouTube topic on differentiation, partial differentiation and differentiation. So this has something to do with mathematical economics basically. Now a specific functional form that satisfies these properties is constant relative risk aversion. Okay, so the example is given by 2 here. So this one is constant relative risk aversion. Okay, CRRA. Now, if you look at this, you have parameters of sigma, isn't it? So sigma is a coefficient, okay, or a parameter of relative risk aversion. So when you have sigma, then you can also have reciprocal of sigma. Now, reciprocal of sigma is actually the term, and specifically it is the elasticity of intertemporal substitution. Okay, so because in the study of OLG here, all right, we have two different types of consumption, during young, during old. Okay, so that's why we have intertemporal in terms of time. So some people may want to consume more during young, less, saving, than during old they consume less, isn't it? Or the other way around. So this one can measure that. Okay, but to be more specific, later, it is actually a measure of an individual's willingness to substitute consumption over time. In this case, between youth and between old age. Okay, so if we have so the value of sigma here is positive, but if let's say we have a specific value in which sigma equivalent to 1, yeah, so what happens to our utility function if sigma equivalent to 1? You try to substitute it back into the utility function into, okay, then it becomes like this. You can have logarithmic function, specific types of function, okay. So this happens if sigma is 1, okay. So, and then, okay, in the OLG, in the basic OLG here, the problem of a young individual or household is basically to choose the consumption profile, okay. What's the consumption profile? That is CT and also DT plus 1, consumption during youth and consumption during old age over her lifetime, as well as her saving, denoted by ST. I guess. Why? Because he wants to maximize he wants to maximize his lifetime utility in expression 1, okay, which is this. Okay, he wants to maximize his utility in expression 1. Okay, subject to what? Subject to the budget constraint, because you cannot just maximize your own utility and you say that I can eat anything without money. So you still have, budget constraint during youth and also old age. So the budget constraint during youth is given by expression 4. The budget constraint during old age is given by expression 5. Now, if you look at expression 4 here, budget constraint is given by consumption during youth is equivalent to the wage rate during youth, okay, received during youth minus saving made during youth. And if you look at expression 5, it is about consumption during old age is given by amount of saving plus the return to saving, isn't it? Now, let's use simpler case to do, optimization. And then the basic idea is we use OLG. We start with micro level in the economy. From micro, we try to transform it to macro level. In other words, in OLG model that I'm going to present to you using simpler case in expression 6, I'm trying to show you that if we have, micro level setup of economics with their utility preferences, with certain conditions and whatnot, how this, individual utility, when they try to maximize their own, satisfaction, can bring economic growth in the OLG model. Okay. Now, so we're going to use the simpler versions of utility function. So let's say we have utility function of a person during youth. So he has, this is logarithmic function also. Why do we use logarithmic function? Because in terms of calculus, it's the easiest thing that we can do, and it's easy to get to do optimization compared to other types of, mathematical function. Okay, so here we have this. This is basically ln CT, remember? Okay, we have 6, isn't it? And then beta here, I did mention to you earlier, beta is a discount factor and the value is between 0 and 1. Okay, and then we have ln what here? So plus beta ln, okay, dt plus 1, isn't it? Ln UCT, sorry, ln dt, u dt plus 1. Okay, so now what should we do? wait a minute, I need to fix something here. So this one, even if it doesn't exist, it doesn't matter. Okay, now, so the idea is this individual person or household wants to maximize utility, and what his choice variable. In other words, what's the argument in this utility function that can be used to maximize his own utility. Usually, wage rate is given because we assume that the firms is producing in a perfectly competitive market. So wage rate is usually following the market rate. So this one we don't have to care. We don't need to optimize it. Let the market optimize it based on demand and supply. So of course, as an individual household, we don't maximize wage rate. We just want to maximize what? ST, okay? And in the end, we also want to find what's the level of consumption that can maximize our satisfaction during youth, and also during old age. Now, what should we do if we want to do maximization? Okay, now let me rewrite again the utility function, the simple case here. So ut equivalent to ln wt minus st plus beta ln in bracket 1 plus rt plus 1 close and then st. So to maximize utility, the argument is st, okay. So what you need to do is that when we do maximization, recall back the basic problem of maximization is to find the first order conditions. So what's the first order condition? You need to know the argument here. What do you want to maximize? You want to find the optimal level of saving that can maximize your utility. So in this case, differentiate utility function with respect to saving, yeah, and then equate it to 0. And then when you differentiate, what happens to this? Okay, plus what happens to this? This one you do it on your own because this one is just mathematical or arithmetic operation that I don't need to teach master student anymore. And you equate it to 0 because when utility function reach this thing, this becomes the slope of utility function with respect to saving, isn't it? When it becomes 0, it means the slope is 0 at the maximum point, yeah? Now, how do you know that you have maximized utility? How do you know that when you found this partial derivative of utility with respect to saving, you know that it is a maximum point? Then that means you can always check, the second derivative, okay? The second derivative, when you check it later on your own, yeah, then you can get it's less than 0. That means the curve is concave. When the curve is concave, it looks like this, okay? So it is you are maximizing. So later, once you do this, okay, and equate it to 0, you rearrange it so that you bring st on the left hand side and the rest on the right hand side, because you want to get what? You want to get the optimal level of saving. So optimal saving is given by what? So later you need to do it, yeah? So here I just show you the final answer, WT. And then let's say we write it S, with S rate here, WT. And where S bar is equivalent to beta 1 plus beta. Okay? Now, so if you look at this S bar, yeah, beta, we know that it is between 0 and 1. So, and then 1 plus beta is actually more than 1, isn't it? Because 1 plus something between 0 and 1 is more than 1. But because beta is between 0 and 1 and beta sits on the numerator, so you know that this one is also between 0 and 1. Beta over 1 plus beta is also between 0 and 1, isn't it? So what is this actually when I write it as S bar? It's actually the portion of wage that goes to saving, okay? So it is a portion or proportion of wage that goes to saving, okay? So saving is actually proportional to our wage income, isn't it? Okay. Other than that, okay, we have found the optimal saving. You can also find the optimal level of consumption. So optimal level of consumption, when you try to calculate later, you're going to get this. Now, I give you an answer here, but you have to do all the calculus and you have to show it, yeah, if you are asked in any exercises. So let's call the first equation here, saving, as equation 7. This one as equation 8. Okay, now we can also find dt plus 1, the optimal level. Okay, so it's gonna be, something like this. 1 plus RT plus 1, isn't it? S bar WT. Okay, so you can see that the next period, or the old age consumption, is actually, the amount of saving and its interest earning, okay, that we earn after we save some portion of income that we earn during youth, isn't it? So if you rearrange it, you can have something like this. Okay, so I cross multiply, then I can have something like this, equals to S bar WT. So when I arrange it this way, and I call this one equation 9, yeah. Okay. Okay, let me use different marker then. So we have optimal saving. We also have optimal current or consumption during youth. We also have optimal, consumption during old age. Now, if I choose this, and this, okay. Now, here, all the value are in present value term. So that's why I write it this way, cross multiply, because I want to write it in the present value term. Okay, now, according to equation 7, 8, and also 9 here, households will optimally save a fraction of what? A fraction of S bar, where, like I said earlier, S bar is actually between 0 and 1 because of this reason. Okay, so household will optimally save a fraction of S bar of their labor income in order to finance their future consumption needs. So they consume only a fraction of 1 minus S bar, isn't it? So 1 minus S bar is consumed from their labor income when young. Now, the saving rate, okay, you look at the saving rate here. This is the saving rate, which is this, okay? And here you can see that the saving rate is actually equivalent to the marginal propensity to save in this context, in it, MPS. And you can see the saving rate consists of discount factor. That means the saving rate S bar is actually determined by the discount factor. Now, it is obvious that a more impatient, without sabar, okay, more impatient individual, lower B is better than, in this case, his saving in terms of proportion of his income will be reduced. Okay, so notice, however, that the interest rate does not affect the amount of income that each individual will save. So how can we explain this result? In order to understand the intuition for this, yeah, it is useful to see the maximization problem with the general utility function in 2. Okay, so recall back the general utility function in 2, which is given by this. Okay, but anyway, okay. So recall that the logarithmic function is a special case for which, sigma is equal to 1, isn't it? So now, so here, if we try to show, the economic intuition for what happens to, interest rate and how it does not affect the amount of income that each individual will save, like I said just now, it will be useful to see the maximization problem with the general utility function into CRRA. Yeah? Now, so This will show us that the irrelevance of the interest rate is a special case that appears only with the logarithmic utility. So how we are going to show this? To assist in the explanation, let me rewrite again the utility function in one. So ut equal to uct plus beta u dt plus 1. Yeah? So this is equation 1 that we already saw earlier. And then if we have CRRA utility function, then you have ux equivalent to x to the power of 1 minus sigma, and then minus 1 divided by 1 minus sigma. And here we know that sigma is more than 1 in it. Okay, now, so this one is 2. What you need to do is that, in order to explain how, okay, in this case, interest rate, okay, here, does not affect the amount of income that each individual will save, then we need to do some, FOC or first order condition. But in this case, you substitute 2 into 1. After you substitute 2 into 1, and then you need to find this, yeah? You need to find this. Equate it to 0 so that you can find optimal level of saving. So you do this on your own. I won't show you how to do it, but you must do it. Then the optimal level of saving after you do this FOC, yeah? And then this is basically optimization. Okay, then you should get something like this. ST equivalent to 1 over, okay, 1 plus beta to the power of reciprocal of sigma, the elasticity of intertemporal substitution, okay, times 1 plus r plus rt plus 1, okay, to the power of sigma minus 1 over sigma, okay, and then the whole thing's here multiplied by WT wage rate, okay, and then we have, when you simplify it, okay, then this one is actually saving function as a function of interest rate, isn't it? Saving rate as a function of interest rate multiplied by the wage rate, okay. This is actually the generic function. It's like, f as a function of rt plus 1, okay. Why? Because this is just the matter of simplification of writing this. Otherwise, I have to rewrite again. So you can see that saving, actual saving in, during young is actually some portion, a portion of wage rate or income. And that some portion is this. And that some portion is actually saving rate, remember? And that saving rate is a function of interest rate. That's how you read it. So that's why I write it this way. Okay, now, and from here, let me erase first so that it won't be a mess. Okay, so from here, we can establish certain things, yeah, so here, right, now I write using right pen. Okay, so when you take the first derivative of SRT plus 1, yes, the saving rate here, okay, then you can see that it becomes positive, okay, if what? If the sigma is between 0 and 1. You can try and check whether it's positive or not, yeah, the saving rate. It means this one, you differentiate it with respect to RT plus 1. Then you can see the sign is positive if sigma is between 0 and 1. And the sign will be 0 if, okay, and only if sigma is 1. And the sign will be less than 0 if, okay, sigma is more than 1, okay. So you can see that the different effects is generated by the relative importance of substitution, which is given by the sigma, the value of sigma, the relative importance of what? Of substitution and income effects in the decision-making process. Now, to understand these effects, let's say consider an increase in RT plus 1. So, RT plus 1 increases. Okay. Now, this will increase the return on saving in it and will induce the individual to increase her overall saving. Okay. Now, alternatively, substitute future for current consumption. Okay. This is the alternative, and this is what we call the substitution effect. Okay. Now, but the individual will also want to smooth her consumption profile over time. So she can achieve this by increasing her first period of consumption as well. In order to, increasing her first period of consumption, then he needs to reduce, okay, her saving, and this is what we call the income effect. So when sigma is between 0 and 1, like in the first case here, okay, that is when the elasticity of intertemporal substitution, okay, if this is between 0 and 1, then it means this one, which is the elasticity of intertemporal substitution is above 1, okay. If this, that means this one above 1, isn't it? Okay. Then the implication is that the substitution effects dominates and the saving rate increases following an increase in the interest rate. Okay. However, when we look at the third example here, when sigma is greater than 1, also means that when the elasticity of intertemporal substitution, which is 1 over sigma, or reciprocal of sigma, is below 1, isn't it? Okay. When we have this one happens. Okay. So what's the effect? What happens here? Okay, then the income effect dominates and the saving rate falls following an increase in the interest rate. Okay. Now, what about if sigma equivalent to 1? Now, when sigma is equivalent to 1, okay, 1 over this also equivalent to 1, isn't it? Then this is the case of unit elasticity of intertemporal substitution. Okay. Then we can see that income and substitution effects are of equal magnitude, isn't it? And cancel each other out. Now, this results explains the results we found in equation 7 previously. Okay, recall by equation 7, this one. All right. Now, okay. Now, that's why, in equation 7, when sigma is equivalent to 1, okay, then you can see SRT plus 1 is actually equivalent to this, isn't it? Then you can't see RT plus 1 here. Now, saving rate is no longer a function of interest rate here when sigma is equivalent to 1. But if sigma is more than 1 or between 0 and 1, then you can see clearly, okay, saving is a function of interest rate. Okay, so that's all for the setup on the individual household side. Now we move to the firm. Okay, let's talk about firms. We have in the economy, we have a huge number of competitive firms. So we have large mass of competitive firms, let's say 100,000 or whatever, but we normalize it to 1 for simplification of calculation. And all of them use capital KT and also labor LT combination so that they can produce output according to Cobb-Douglas production function below, which is 10. Okay, and we already know that it's this type of production function or technology and variations of it has been employed repeatedly in our previous lectures. So its characteristics have been discussed in our analysis of the Saloon model. Now, because of this reason, here we are just going to summarize its implications. So first of all, okay, In terms of output per worker, we have this, isn't it? Small letter of YT, which is YT over LT. Okay. And because of this, we can rewrite expression 10 here as something like this. Output per worker equivalent to A KT alpha, and this one is expression 11. Not only that, okay, profit maximization under a perfect competition implies what? Implies that equilibrium wage and return to capital are equal to what? So let me write it here. Yeah. So wage rate, equilibrium wage rate is given by this. I'm sure you have seen this one. Okay, A KT alpha LT minus alpha power, and then you can rewrite it in the per worker term as this 1 minus alpha A KT alpha. Okay, so this one we name it as 12. Okay, and also we have written RT equals to, okay, if I write it after simplification, alpha A KT alpha minus 1, and this one is 13. Okay, and we know that this function is a constant return to scale function because it is a Cobb-Douglas function. Therefore, this implies what? So output per worker is actually equivalent to labor equivalent to 1, yeah? Okay, times WT plus RT times KT. So whatever being produced, exhaust with whatever being received by all, inputs of production. Okay, now, and also, yeah, you can see LT, okay, fine. All right. Now, what about financial intermediaries? Okay, so for financial intermediaries here, all of them are perfectly competitive, and they use the deposited savings by households, yeah, as inputs in a technology that basically transforms units of output at time t, okay, at time t into units of capital at time t plus 1. Okay, so then we can have expression, okay, 15 here. Okay, we can have expression 15. Before I say 15, this one is actually 14, yes, so we have 15 here, so that you would be confused. So expression 15 or equation 15 states that aggregate saving in time t, yeah, so this is aggregate saving in time t, is actually equal to, all right, aggregate total saving. ST is just for one household, so total saving is actually total population times ST, isn't it? NT-ST, okay? All right, so these savings are the inputs toward the formation of the economy's future capital stock, which is this. Okay, so this is 15. Now, next, we want to look at the dynamic equilibrium in the OLG. All right, so how do we do it basically? For the dynamic equilibrium in the OLG, basically, now you can see before we go into detail on the dynamic equilibrium in the OLG, we have seen the household side or the individual sides with their preference, utility function, and then optimal saving and whatnot. We also have seen the setup for reforms and how they maximize profit, how they decide to retreat, how they decide the return to capital. Okay, and then we have seen the financial intermediaries as well. So we have three things here. We combine all of them because we want to see the dynamic in the equilibrium OLG. Okay. Once we have the dynamic in equilibrium of all in the OLG, we can come up with the law of motion equation. Yeah. Now, so how to come up with the this? Let's begin with this. The equilibrium in the labor market is given by 16. Yeah. So NT equal to LT. The number of population is actually equivalent to the number of workers in period T. So this is very straightforward to explain. Yeah? Recall that only the young households, of which there is a total number of NT, isn't it, have the ability to work, because the old adults, they don't work. Each of them has a unit of time, has 1 unit of time. Thus, aggregate labor supply is NT also. So, of course, aggregate labor demand is LT, a unit mass of firms. Each firm demanding LT units of labor. Now, the condition that the demand for labor is equal to the supply of labor is thus represented by equation 16, isn't it? Okay. So here, population is this, number. Demand is this number. So that's why we have equilibrium in labor market. That's what it means. Okay. Now, note that one implication of this is what? Okay. One implication from this is that we can have, let me write it here. Output per worker equivalent to KT, equals to capital YT over NT, isn't it? Instead of LT, because now NT is equals to LT, and capital per worker is actually KT over NT as well. Now, and we also have the growth rate of population and also labor, yeah, is this, we call back this. Okay, so here, as a consequence, okay, we can have, output per worker in the next year is actually equals to what? Equals to saving, okay, in that year, in that current year, over 1 plus n, isn't it? So I call this expression 7. Okay, so basically you know this, plus whatever information that you have previously when we have household and whatnot, and we can come up with law of motion equation. Now, the ST that we have previously, if we can recall back, okay, the ST that we have previously, you use ST that we calculated when we have something like this. Okay, and then you have this. You use this ST, put it back here, okay, and then you have WT from the previous slide, which is this, yeah, which is this, you have WT, and you have ST, okay. Substitute WT into this, then you get this, substitute it back into this, then you get this. Then you get what we call first order difference equation or law of motion, which is expressed in equation 18. Okay. As we can see, the dynamics in 18 here are expressed in the form of a first order, and it is nonlinear. How do you know it is nonlinear? If you differentiate, you can see alpha here. Okay, when you differentiate it once again, you can see, okay, delta F over delta KT here is gonna be like this. So you know it's nonlinear, because if it is linear, then the second derivative is not this. The second derivative will be equals to 0. That's basic maths that you have to revise, yeah. Now, anyway, so it is nonlinear difference equations, a form of capital accumulation that we dealt with and analyzed repeatedly during our previous lectures, isn't it, or previous videos. Okay, so the derivation of the long-run equilibrium should be very straightforward actually, because now it is more or less like the same, first order difference or law of motion equation that you have seen in Solow model. Okay, so we can summarize this through the following propositions, yeah. Okay, so proposition 1, what does it mean by proposition anyway? It is a results from the calculation that we made. So this is the way we present results in theoretical paper. If you have econometrics articles or papers, You don't say it's as a proposition, you say that results discussion, result section in it. But here we call it proposition. And what are the things that we want to put in proposition or in the results of theoretical paper? For this specific case, we want to know the results of how many steady states in this case. Are these steady state equilibria stable or not? Okay. So based on this proposition, we have proposition 1. Okay. There are two steady state equilibria that satisfying Kt plus 1 equal to Kt equal to K star. Now, you look at this, you have seen this condition for steady state, isn't it? This one is the steady state condition that you have learned in the Solow model. Okay. Now, what are the two steady state equilibria? The first one is Ka at the origin. So when it is at the origin, so you can see that Ya is also 0 because if there is no capital per worker being used in the production, there is no output produced. And the second one is Kb given by this. Okay. Now, if Kb given by this, what is Yb? Can you find it? Okay. Now, how to prove this, that these two are the, equilibria? Okay. And here. So, from this equation, equation 18, okay, I'm showing you the proof, okay. It is very obvious that, okay, Ka is equals to 0. How do you know? You look at equation is, you know that the condition is Kt plus 1 equal to Kt, isn't it, when it comes to first order difference, when you want to find steady state. Yeah. So if this one equals to this, one possibility is you put this one 0, multiply by the whole thing, this one also 0. So that's the first steady state. Okay. Now, the second steady state is this. How do you find it? Okay. If you know how to find steady state in the basic Solow model, then you know how to find steady state in this model also because it's just the same thing. Now, I leave it to you to find it because I already gave you the final answer. So it's your job to find how to get this from equation 18. Okay. Now, so that's how we prove it. Okay. But of course, you have to write your own sentences here. Yeah. I won't show you how to write sentences for proof. You have to learn it. Okay. Now, are they stable or not? So you have to check Ka. This one, is it stable? You have to check Kb equivalent to this. Is this stable? Okay. Now, for your level up to this point, one way to check it, like I said in the Solow model, is to see, okay, if Fka prime, okay, is it, between 0 and 1 positively, for instance. Okay, what does it mean by this? Okay, is it greater than -1? Okay, or then this. So you check this. This one is, there's a lot of YouTube video shows you how to check stability for any kind of point in a graph. And I want you to show it using this. And another way to show it is by looking at the graph. So we need to show the graph here. For the graph, we need to show the 45-degree line, which is this, where we have Kt plus 1 equals to Kt, and then you have Kt plus 1 equals to Kt here. Okay, now, if you check this one, check all the properties like the way we did for Solow model, yeah? Check this, what happens? Check this, what happens? Check also this, what happens? Check this, okay? What happens? And so on and so forth. You have seen this one in the previous video. So when you check all of this, then you can draw the law of motion equation. After you check all the properties of the first order difference equation in the previous slide, then you can start to draw it based on the properties that you have checked. So when you draw it, it looks like this, yeah. Okay, now, so this is our fkt, which is equivalent to kt plus 1, isn't it? Now, so you have one point here, okay, as your steady state. Okay, then let's call this point as K1. You also have another one here at the origin, and then this is K0, K0. Okay, so you have two steady states basically. Okay, now you can check whether this steady state is stable or not. Yeah, so you have to check it. Okay, like the way we did for Solow model. So, and let's say we want to check in the form of graph. Okay, in the form of graph, let's say your initial condition of capital power K is here, KA. So you can see it's obviously on the graph it is here. And then what will happen is that there will be adjustment towards, steady state. Then you can see that it moves to point A. You can also check if your, your capital is at KB here. And then you can see the process also move to point A. So based on graph drawing, it is stable. But formally, how do you check it? Like I said previously, you have to check from, maths book on stability concept. And we also need to learn how to check it if you're given first order difference. What's the condition to say that this steady state is, stable steady state, and this steady state is not stable steady state. Okay, now so basically here what I want to summarize is that you can follow the same steps as in the Solow type models. Yeah, we have solved in the previous video. So we get this kind of diagram. Okay, so if you look at this kind of situation, okay, there is another question on this. Okay, we have some questions to address. So what are those questions? Why in this economy, okay, this economy is unable to sustain, okay, positive growth in the long run? Okay, what's the reason? Because as you can see, every time you are away from steady state, there is growth rate here because there is this equilibrium. Then after that, growth rate becomes smaller and then reach point A, isn't it? Then stop here. That means growth rate at point A is 0. Okay, if we recall back in the study of growth, Solow growth model, G is 0 at point A, isn't it? Because the graph is similar. And you have to look at also, if you go back to the first order difference equation here, you can see A, you can see alpha, you can see beta, you can see n, other than kt, isn't it? How all of these parameters, okay, affects, okay, the long run level of per capita, long run level of capital per person. So can you explain the intuition here? Now, in this example, okay, we know that we have steady state situation, okay, similar to the first example of Solow growth model. Is it possible for us to create, instead of steady state, to create economic growth in the OLG model of growth here? Is it possible or not? Now, you can try by using the same type of production function that I introduced in the second video of Solow growth model with technology. Yeah, so let's recall back. I did modify a little bit the production function where we have yt equals to a kt alpha, and then in bracket ht lt 1 minus alpha. Okay, and then we assume that, okay, technological progress grows at a positive rate of g greater than 0, yeah, over time. So that means, okay, so ht plus 1 equals to 1 plus g ht. So this is another assumption, and this is not a new assumption because it has been introduced in the previous model of Solow and also technology. So it can be shown that at the steady state, the growth rate of capital and output per household are equal to the growth rate of technological progress, isn't it? So, and can you explain why here? So this is what I mean just now. So kt plus 1 over kt minus 1 equals to yt plus 1 over yt minus 1 and finally equal to g. Okay, so in this case, once you have this, can you replace the production function that I introduced in this OLG model, which is this, yeah? Okay, let's go back to the firm's production function, which is this. Okay, so this is the initial production function that I introduced for OLG. But now, let's use this one. You use this one, and then you recalculate again the kt plus 1, and then you have this assumption, yeah, this kind of assumption. Okay, and then you try to come up with kt f kt. Okay, what is it do you have? And then you try to come up with kt plus 1 over kt minus 1. What do you get here? And is it equal to g or not? Yeah. Okay, so you try this. If you know how to do this, and you refer to the Solow model, yeah, and then that means you also can understand that any kind of growth model, if you wish to come up with, growth or steady state, you can modify the model either, by modifying our production function, isn't it? Or sometimes, okay, this is just extra knowledge, yeah. Sometimes you can also create growth or steady state by modifying the utility function. Okay, this kind of things is usually learned more when you read a lot of articles. So that's why purposely I gave you project paper on endogenous growth or utility function being incorporated in production function to create economic growth and whatnot. Okay, I know it's difficult, but this is the way for you to realize that outside there are some master degree for economic study in which they already go in depth when it comes to the macroeconomic theories. Okay, so before I forget, the topic that we have here, which is OLG model of economic growth. Okay, for this, yeah, you have to understand that this one is, there is no specific textbook that I refer to when I teach you guys, because overlapping generations model for this simple one here, most of them in the textbook are using continuous time, not discrete time. Okay, so as long as you can compare and contrast with this kind of lecture note with any journal articles that are using discrete time, in particular where they use OLG and also production function to create economic growth or to create first order difference. You do a comparison between these notes and also their papers, then you can see how OLG is a very rich model in the sense that they can